Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing tunnels, their concepts and configuration in Junos. In this lesson, we'll be covering these situations where a tunnel configuration would be applicable, and some considerations to keep in mind when planning or configuring tunnels in your enterprise environment. So, let's jump in and get started with reviewing what an IP tunnel is. At its most general concept, an IP tunnel creates a communication channel such that two networks may communicate. Typically, this is done to allow separate networks to communicate over some intermediate network, where the traffic would not be directly routable. An example of this would be two offices of our enterprise, where private RFC 1918 addressing is used in each office, and they are connected by a public internet service provider. Since the RFC 1918 addressing is not routable on the public internet, a tunnel may be used to encapsulate the IP packet within another IP header, which is routable over the public internet. This can allow the offices to communicate without the use of network address translation, or NAT. An important note that is often confused by network professionals is that a tunnel does not necessarily mean the inner IP packet is encrypted. Many of us are familiar with VPNs, which may use encryption protocols like IPsec and SSL, though the configuration of a tunnel does not require that the payload be encrypted. We mentioned tunneling involves encapsulating the inner IP packet, so let's take a closer look at that concept. So, we mentioned that IP tunneling involves encapsulating an IP packet so that it may traverse some unroutable intermediary network to reach some destination network. In our diagram here, we have Site A and Site B, which are interconnected by the public internet, represented in the middle. If Site A is sending an IP packet to the destination machine at Site B and will traverse an IP tunnel, then the router here at Site A will encapsulate the packet in an outer IP header and a tunnel header. The tunnel header includes some control information about the tunnel itself. When the router at Site B receives the packet, it will strip off the outer IP header and will inspect the tunnel header. This will associate the packet with the tunnel and allow the router to then forward the packet onto its destination within Site B using the inner IP header. In the next slide, we'll review some of the use cases or applications where tunnels can be used. As we mentioned earlier, IP tunneling can allow packets to traverse networks that would otherwise be unable to route that protocol. In the previous example, we had IP packets which were addressed with RFC 1918 IP addresses that traversed the public internet with a tunnel. However, even non-IP packets could be tunneled, or IPv6 packets for that matter. These are just some of the use cases for IP tunneling. Now, we have mentioned IP tunneling a few times, and there is indeed a Junos tunnel type called an IP in IP tunnel, which encapsulates IP traffic in another IP header to traverse some intermediary network. Another tunneling protocol available is generic route encapsulation, or GRE tunneling. GRE tunneling is generally a bit more flexible and can encapsulate non-IP traffic. In the example below, we see that MPLS traffic, IPv4 traffic, and IPv6 traffic could be bridged between sites by using a GRE tunnel. Let's move on now to some of the considerations that one should make when implementing IP or GRE tunnels. First up, it's important to note that by default, IP in IP and GRE tunnels are stateless. This means once you configure them, they will start encapsulating and sending off traffic. They do not know nor care whether the other end of the tunnel is active or alive. As long as the local device has a route towards the destination of the tunnel, then it will be in an up state and sending encapsulated traffic. BFD and some other protocols built into various specific tunneling applications can provide the tunnel with a keep-alive mechanism. Though by default and at its most basic configuration, both of these tunnels are stateless. The next consideration to take into account is packet fragmentation. Typically, network engineers don't need to care about fragmentation, at least not much. This occurs when the MTU, or maximum transmission unit, is smaller on a transit segment than on the endpoints, and the packet must be fragmented because one of the segments cannot transmit or receive a frame the full size of the packet. Usually, this is not an issue, although it may introduce some latency as the transit devices fragment the traffic and reassemble it. In the cases of tunneled traffic, this may not work so well. Because of this, you should consider what the maximum MTU is in your transit path, and try to ensure the tunneled traffic will not be fragmented. Especially with the addition of the tunnel header, this can cause some complexity in your MTU calculation to ensure this is taken into account. Finally, when configuring an IP or GRE tunnel, ensure that the destination of the tunnel does not end up having a route that is through the tunnel itself. This can occur easily if you're running some dynamic routing protocol over a tunnel, and the WAN interface is a passive interface in the protocol. This can cause the remote end of the tunnel to learn a route to the termination point of the tunnel, which travels through the tunnel itself. This will cause the tunnel to flap continuously, significantly degrading your performance. Finally, let's take a brief look at some requirements for tunnel configuration. Both GRE and IP in IP tunnels use IPv4 networks as the transit network. Because of this, though it may seem obvious, a requirement is for the two tunnel endpoints to have IPv4 connectivity between them. Another way to say this is that the source and destination address of the tunnel must be fully routable as IPv4 addresses. The last item here is less of a requirement and more of a property of the tunnel configurations in Junos. GRE tunnels are GR interfaces, as we see here. Simply configuring a GR interface and setting the tunnel properties, as we'll see in another lesson, is sufficient for creating a tunnel. Similarly, an IP in IP tunnel is created by using an interface name with the IP prefix. This concludes the tunnel applications and considerations lesson. I hope that this lesson has been informative for you, and I would like to thank you for viewing.